So in the past several lectures, I discussed all the ingredients required for the quantum mechanical part of the subject, and now I'm going to change over to describe the ingredients needed from the computer science part of it. Again, it will bring in a lot of concepts which need to be understood from, well, the basic logic process or thought process. And again, if you are looking for details, there will be books written on it. So I'm not going to go into all that detail. I will finish it probably in a couple of lectures, whatever I want to say, but try to understand the logic of the whole structure. So the subject generally is discussed under the heading computational complexity. What are you trying to do when you want to design a computer? Okay. And I have already mentioned in the earlier lectures that we want to sort of minimize resources while maintaining reliability of the result. Okay. And I have mentioned before that this criteria many times conflict, and you have to find your own judgment, trade-off, whichever way you want. But this is the goal. Well, if you can find a result doing less work, of course it is desirable because we don't want to waste our effort. But in the process, we don't want to give up that the answer will be completely haphazard. We want the answer to be still available in some form or the other. And this structure now tells us we have to quantify everything. What do you mean by resources? What do you mean by reliability? And the whole exercise is quantification of this general feature. So what we know is that physical data can be represented by mathematical variables, many times labeled as information. There is a map, but we kind of construct it in our head that this connection is possible, and this allows the important feature that what is a mathematical algorithm and what is a physical system. We are kind of accustomed to using this, but there has to be a connection between the two at whatever level. We need to figure it out, but the fact that we can do that is a great help. Because you kind of work on one without worrying about the other most of the time. And you have to still keep in mind that the efficiency of whatever you want to do will still depend on both these things. You can write a good code, but then you have to also worry about whether a good hardware is available or not, and vice versa. You might have a good hardware, but you don't have a good program. So ultimately, many times you have to come back and you, in some sense, optimize this and optimize that in some sense or the other. But this is a point which allows you to now sort of separate this criteria into what is done in the software and what is done in the hardware. Okay. So let me write down some simple-minded things. That what is the software resource? And there are generic labels. Something can be called a space, which is number of variables, size of memory, etc. You need so many things. And other important criterion is time, which is number of algorithmic steps. How long before we get the answer. Okay. And one can add some more things if you have additional features. One of them, which is often labeled, is something which is done in advance and it's available. Somebody has made a dictionary, okay? And all you have to do is go and look it up to find some results. The dictionary is there, you can use it, somebody else can use it, whatever it is. It's stored in some place. And then the software resources can be said that number of consultations. How many times you are going to go and look in the dictionary. And computer science word for that is oracle, which comes from Greek history, where you essentially go and ask a priestess, in our context, like an astrologer, what is it that I have to do, and some answer will come and you will follow that. That is a number of consultation. So this can also be taken as a resource, and you have to count all those things, whatever it is, in some manner. And we know that these all can be counted as integers. It's important. They are not real numbers. They are all going to be integers, and you will label them, okay? So you can say 1, 2, 3, 4, what is larger, what is smaller, etc. And there are trade-offs which are possible. For example, in parallel computers, you increase the space, lots of boxes or cores these days doing things simultaneously, so the time comes down, but the space goes up. Okay, so those kind of things are possible. What about the hardware? And here again you have to think. And one part of the hardware is the mapping between these two. Okay, the software part generally never worries about the mapping, about how the system is going to be converted, and the mapping is generally some sort of language. You need that, and of course you need a language which the hardware will understand. So you have to figure out what is the good choice. And another feature is energy. You have to plug in the computer into an electrical socket for it to run, otherwise it will not do its job. And it's a parameter, but it's very much a physical parameter, and you have to figure out well, how to kind of optimize it. Again, there will be trade-offs. But yeah, this is going to be connected to what can be called as speed of computation. Just says that, well, if you want the result fast, you have to invest more. Either the better hardware or faster computer will require a clock speed which will run in whatever steps are there, but clock speed is connected, so all kind of things will go inside there, and then you have to spend more energy if you want to do that particular job. And here something which is kind of empirical is, I can only label as availability or convenience. You want to do some job, of course you know that some fancy computer will do it very efficiently, but you don't have it. You will just do it quickly with whatever you have. Okay, that is a choice of hardware, it's a trade-off, but yes, those kind of things happen all the time. So again, trade-off. Possible, and I gave an example of this time in one of the earlier lecture, that how we ended up counting in the decimal system, because the hardware was there, our fingers, to count on, and it was the quickest thing to do without worrying about looking for some fancy device, and that's how the counting started, and we still continue with that without too much trouble because it's there with essentially everybody. You want to get an electrical computer, then you will go to a binary system where there are no 10 fingers over there, but the electrical circuit will say I can put it on and off. And so those two signals are very convenient to map onto mathematics, and then you use a binary system. So the hardware is there depending on what is available, what is convenience, it decides the language, and it decides various criteria about what you are going to do. There are trade-offs all over the place. But these are the features which again need to be counted. Or hardware is not that easy to count. Here the integers are very easy. Here you have to actually look at properties of the physical system and decide. So this is a so it is in some sense going to be more subjective and connected with physical materials, their properties, their transformations, whatever is available to us. Okay. So this is the broad structure, and now we have separated various things, and now we can look one by one about what all things happen. So that can be now quantified a little more carefully. And the first notion which we need to understand is the concept of computability. You have some mathematical procedure, but what can it do and what it cannot do? Both these features are to be understood. And there are surprising things over here, that there are things which you can mathematically define, but you cannot compute. So there is a specific structure which specifies this is all you can do in some sense. And that needs to be understood, and the answer to that was provided by Turing in a rigorous framework. So Turing defined what has been now called a universal computer, or more commonly a Turing machine. Okay. What is the meaning of universal? It means that it can do what any other computer can do. Okay. And that is the sense in which it defines what is computable and what is not computable. If the problem is computable, Turing machine can solve it. That's the end of the story. So it's a powerful result. So what is the construction? So it's a mathematical structure. So this machine has a several different components. There is what you call a tape, which is infinite. It has data written in so it's a long one-dimensional structure which is divided into distinct cells. Why distinct cells? Because we are going to play around with integers. And in each little cell, some data can be written. The important point is that tape is infinite. So you can take it as integers going from minus infinity to plus infinity. And yeah, to go a little bit ahead of what I was trying to say is, if it is finite, then the universality is lost. So it is necessary that the tape is infinite. Then there is an external head or a probe which can read from the tape, or it can write something on the tape. Okay. And it can move on the tape, left or right. This is again system which is buried in some sense or the another in all the memory which is there in the computer. You can go and look up what is here, there, etc. You can read something, you can write something, etc. Everything is available. And then there is what can be called as a state of the machine, which is a program. It's finite. To do something depending on the data on the tape, and it's so this is also finite. So the machine is in a finite number of states. What does the program do? It reads something from the tape. Depending upon its own state, it will decide what to do. What is the decision? It can move left or right, or it can write something on the head, or it can even stop. Something the program has completed, now I will just write down the answer and stop. So this is all is again a system. Important point is these are called all finite ingredients. Sometimes you referred to as a finite state machines. So, okay, these are related concept that if you make this tape finite, whatever this is reduces to something called a finite state machine, and they are not universal. So, yeah, again, you have to choose some things for how you are going to write the data. So, again, this is a finite set of symbols. Some language has to be constructed to write something on the tape. And we can choose some alphabet or whatever you want to work with. So this is a definition of this Turing machine. And the best thing is to, well, look at how some simple problems are solved on it, and then at least get a rough concept that yes, it can do what a computer algorithm is supposed to do. So I can give an example. Very simple example is a find parity of the binary string. Binary string means that the variables are only 0 or 1, and parity means that the number of ones in the string, they are odd or even. It's a very simple task, and we can immediately construct an Turing machine program for it. So what you have to do is create a tape some symbols and mark the endpoints of the string somehow or the other. I am using the symbol E, which is allowed as some representation of the data. It just means that the string starts here and ends over there, some number, and in between there are some zeros and ones and all kind of things. Okay. So how does the machine do its job? That it will start here, or rather it has to say that I go to the left side of the tape, find this endpoint, and that is my starting point. Okay. Then it will move, after discovering the E, move one step to the right, look at what the symbol is. And as I said, you are just going to do a very simple task, find the parity. So you have to say that the internal state of the machine is initialized to 0. So then it finds the first bit. If it is 0, what is the instruction? It will iterate continue moving towards right. Don't do anything else. If it is 1, again continue moving to the right, but flip its internal state. Okay, it has a 2 state, but now the internal state will become from 0 to 1 if it encountered 1. And continue onwards. So every time one is found on the tape, internal state is flipped. And keep on doing that until you hit the final E, and that says that the string is finished. So then the machine's job is in the next square, write the variable of its internal state and stop. Okay. And that whatever it writes, so at the end, and that completes the program. So it's a very simple thing, but it shows that yes, you can do some type of computation. If you want to make a problem little harder, then say that I don't want to just find the parity, but I want to find the total number of ones in the string. Okay. Then the number of instructions will have to be kind of remain finite. Remember that the tape is infinite, so I cannot write the number of ones in the internal state because it will keep on growing. The internal state of the program has to be finite. So the number of ones which I want to count actually will be written on the sum square of the tape itself. And you can choose, you find a 1, you go and put it at the end, then you have to come back and start again from where you left off. And then the machine will go back and forth. If it found 1, you put a counter here, add 1. To come back, well, you have to know where to come back. So then instead of 1, I have to put a new symbol that I have already read this place. I don't want to read it again. So you can change the, say, number 1 to R, some letter of the alphabet. Again, it's finite is allowed. So I write something, come back all the way till I have an R, and then again start searching for which there are another 1 left over, which I can go and add to that particular number. And here will be you have to construct a binary representation. When you add 1 plus 1 plus 1 plus 1, how many times, and you have to write a little code for doing that. It's possible, it's not any different than what you did in primary school, but that is something which can be done. So there is a back and forth movement some new symbols are needed for more complex task. So this is a kind of a very elementary construction which Turing came up with, but the important point is that it can do what any other computer can do. And that is a powerful principle which now goes under the name of Church-Turing thesis. Statement is quite simple, that I will write it in a computer science kind of wording, that every function that is naturally regarded as computable can be By the way, Turing was the student and Church was his advisor when this thing was constructed. So this defines what I set out to explain what is computable. If a Turing machine can do the job, the function is computable. What turned out to be much more important, but it was realized later, that you have various categories of computers, and the program on the Turing machine is not going to look the same as what will be run on a different computer. And the question then is of how much is the difference between resources of different computers. So the powerful result is that this universal Turing machine can compute what any other computer can do by at most polynomial overhead. Polynomial in what? In the size of the data which is specified on the tape. Remember, all the stuff is finite and bounded, it's fixed and forever. And this is a powerful principle which is invoked in many different senses, is in all kind of computational complexity analysis, that all the functions which are related by a polynomial mapping are sort of one type, and then there can be functions which are super polynomials. The common example is exponential, which are of other type, and you cannot convert between one and the other. And that is, so this is important. For the classification of the problems. Some problem will require polynomial resources, some problems will require super polynomial resources, and even with a universal powerful computer, you cannot convert one into the other. What more? Well, there was a generalization of this thesis, and that was labeled as Church-Turing principle, and it was done by Deutsch to include in this framework whatever happens when you have quantum physics coming along. Okay. Remember, all the stuff, whatever I have described, is basically integer arithmetic, doesn't even deal with real numbers. The quantum mechanics brings along a lot of new things, and then how will you rephrase this statement, and that is what was done by Deutsch, and he shifted the emphasis that you are not trying to compute anything, but you are trying to understand physical property of some system. Okay. So the statement is again every finitely realizable physical system can be not computed but simulated arbitrarily closely, because we are not dealing with integers anymore. By a universal quantum computer, what we do not want to give up is the finiteness of the system, whether it is the head or the program or whatever it is, and that is still true, but the algebra gets generalized, so we are only talking about simulation with sufficient accuracy, and what is that simulation of? It is some physical system. Okay. And this has become accepted statement of what a quantum computer can do, okay, instead of what a Turing machine can do. It can simulate any physical system to whatever accuracy you want. Now, why all this emphasis on computability is another story. and which was a kind of a, what to call, exercise in mathematical logic. And it was a result which was constructed before this Turing's definition came along, and it came as a surprise, and many people would not believe it. And it goes under this generic description that mathematical logic is incomplete. Even today we find it hard to understand it, but the proof is rather straightforward, or rather giving an example of it is rather straightforward. What does incompleteness mean? That any self-consistent axiomatic mathematical framework. What does it mean? That the mathematical rules are precisely defined, and self-consistence means that you cannot find any contradiction in it. The extra feature it requires is that it allows recursion. What is the meaning of recursion? It means it's a routine which can call itself. And it's easy to give an example to specify it explicitly. That suppose you want to calculate a factorial of a number, n factorial. I can write a routine which says n factorial is equal to n times n minus 1 factorial. And then the routine will just loop. I'm given a number n. What is n factorial? Well, keep the number n in the memory and call the same routine with n minus 1. And the routine will have an ending statement. If this n is equal to 1, then number is equal to 1. So this is an example of a recursion. You wanted to calculate n factorial, you replaced it by calculating n minus 1 factorial. The program remains the same, just the argument changes. So that is something which is allowed in a mathematical framework, and it is known as recursion. Has problems for which you cannot find an answer. That's it. System is complete, no contradiction. I can phrase the question in that language allowed by the axiomatic system, cannot find the answer. And that is the interesting part, which just says that there can be something which can be computable and something which is not computable. There is no contradiction anywhere, just you give it into a computer, it will go into an infinite loop. It will never stop. And that can happen with the Turing machine. So it can go into an infinite loop. With all these finite instructions and whatever it is. So how do you understand it? Again, best thing is to construct an example. And the example very frequently quoted in the context of computation is something which is called a halting problem. And the problem is very simple. You have a Turing machine. The program is given. You have a tape. The data is given. The question is that given this program and given this data, tell me whether the machine is going to stop or it's going to go into an infinite loop. And there cannot be a general purpose program which can do this job. That is what Godel's theorem tells you. So, given a Turing machine program, and input data, find if the machine will stop. So that is essentially the problem, and as per the theorem, this cannot be done, and the proof is also very simple, few lines, nothing more than that. You construct a explicit code which contradicts this result. So how do you construct a explicit code? So as I said, the Turing machine, everything is finite except for the size of the data. So some instruction, some alphabet, everything is finite. So any Turing machine can be labeled by an integer, say x. X is and this is, it contains all the what I wrote down, state, all finite over there which I wrote down, program which are the instructions, and symbols. They are all finite. So I will just list all of them one by one. The integer can become large, but they are all finite, and so all possible Turing machines can be labeled by some integer x. So now I define a function which is called the halting function. And it has only two values. 0 and 1, which give me the answer to the problem. This is a machine does not halt, and 1 is this. If the machine halts. And then the problem is to evaluate this function. Remember, x is just an integer, it's a label of the Turing machine, and this is what we meant by the halting problem. Either it stops or not though. And the result is that this function is something that cannot be computed by any means. And the proof is a kind of a simple counter example. So I'm going to write a short program. The language doesn't matter because the statements are very simple. There's a program called Turing with some integer argument. Why? What does it do? Its job is to compute this function for this particular argument. I'll call that z is equal to h of 1. And then the instruction is only this. Z is equal to 0, stop, otherwise go into an infinite loop. That's it, there is nothing more in the program. What is done cleverly here in the program is the assignment here are flipped compared to what is over there. That is deliberate, that is the crux of the logic. So, these values of whatever stop, loop, forever, values of z are flipped. So what will happen? This is a Turing machine. It will have its own integer label. So I run this Turing machine with its own integer label. And then it will stop when it is not supposed to stop, and it will loop forever when it is supposed to stop. So running it, this program with its own program label produces contradiction. And what is the way out? Well, there is nothing complicated in the program. The only non-trivial statement is this, that I can evaluate this function. If it gives a contradiction, that statement must be false. That's the end of the story. So this is a well-known example, but it gives an explicit construction that there are computational problems which do not necessarily have an answer. So this is a kind of very broad background about what we have to consider, and now I can move on to a lot of labels which are used as the characterization of all this counting of resources. This Turing machine already said what is computable. On top of that, it provided a classification that there is something which is different between polynomial on one side and super polynomial on the other side. But then you can give now much more detailed definitions about what are the kind of problems we encounter in real world and what are their characterization in terms of the complexity. So the first job is actually just to label the problems, because we have to decide on what to count. I gave examples, but depending on the particular problems, we will be counting various things. So I'm going to erase some things. If anybody wants to take a photograph, just go ahead. I will remove this particular part. So the problems where the mathematical analysis is the simplest are called decision problems, which means that the answer is yes or no. That's one bit in the standard binary logic. And then what is that characterize the size of the problem, which will be the argument of the what is the resource. So the resources are function of the input data size. What is the number of variables, how much memory I will need, etc. And depending on the problem, it will also say that if the input data is so large, how long will the computer run before it gives me an answer. But that is the only input available because I simplified the output. Output is only 1 bit. And any problems of this particular character are called decision problems. You can ask, well, there are a lot of other problems which are not decision problems. For example, there can be optimization problems, which typically find minimum or maximum of some quantity and that answer is certainly not yes or no. So these kind of problems can be converted into a decision problem. How do you do that? Well, you have to start somewhere. And then continue until you find the extremal value. And the standard way of doing it is you start with a certain range of values, and then as the program runs, keep on narrowing the range until you reach the particular result that you want. Best to give an example. Say I want to calculate value of pi. It's not a decision problem. But I can figure out by some way or the other that value of pi is between 3 and 4. Requires some background estimates. It will be very crude. You are just looking for a bound. And then I can ask the question that I know that pi is between 3 and 4. Then I reduce the range. The question, decision problem will be, is pi between 3 and 3.5? The answer is yes, my range is narrower. Next question is pi between 3 and 3.25. So this is a decision problem. And this sequence of decision problems will ultimately come down sufficiently close to pi, which is what I was looking for, a optimization problem, or here it is actually evaluation, but you can do it with more general problems like find the shortest distance between 2 points. I can put a bound and then keep on asking at every point is the distance between this particular boundaries, or it is on one side or the other side. It's a binary search. And then the complexity will be, I want to evaluate this optimal value up to some accuracy. Okay. Pi, I can say that I want to evaluate up to 10 decimal points. So then there will be sequence, like I can break it down into this binary search, and I will stop until that range becomes sufficiently narrow. I have calculated pi up to 10 decimal points. And what is the total complexity? Well, the total complexity is the sum of all the binary problems that I solved. And that is completely okay. And why this strategy is useful? Because binary search is a very powerful structure in the sense that what is the accuracy if I have something specified by n binary points? It is 2 to the power minus n. So I can narrow the range exponentially by running n decision problems. Okay, so n decision problems give accuracy which is 2 raised to minus n, and I am interested in some particular precision. I get there by adding an effort which is logarithmic in the accuracy that I want. And many times this is affordable because the difference between here and here, which is going into this particular label, the polynomial versus exponential. Okay, so here, yes, the accuracy is part of the output, which was not there. So this is the accuracy, it is the output property. What is the effort? It is log of the precision. Okay, so just like here I am looking for function which is polynomial in the input size, this is a linear in the output size. The amount of effort which I put in, how many bits, that's what it is. And that is very useful, and that's why people don't worry too much about separately classifying the optimization problems. I can reduce them to the decision problems, and it is most of the time quite acceptable. There are also surprising facts, particularly for an example which I just gave, that calculating the value of pi. And there are very clever algorithms. And suppose I want to say that I want a millionth bit of pi. It's a decision problem, because it's just millionth bit. Do you have to calculate the million minus 1 bit which went before that, which is what this binary search will imply? And the answer is no. I can calculate the millionth bit of pi without worrying about what the million minus 1 bit ahead of it are. Doesn't matter. I can directly calculate that particular bit. So there are unusual situations like this in the study of algorithms, and which can actually help when you are trying to look for such a conversion. So that is one part of the problem. Then there are what are called function, somewhat related to this. because the example which I was quoting, like calculating pi, can be considered a function evaluation problem also. Calculate f of x. Some number and in general it will depend number of bits specifying its value, and then the resources are depend on input data size as well as the accuracy of the output. So it becomes a function of two variables. The input data size was something which was already there. You add another label for the output accuracy, whatever it is, or the log of the output accuracy is the number of bits you require to specify the output. That is a little more general situation. Then there are these problems which I mentioned. Earlier, which used pre-computed results. Where you count the number of consultations and these problems are called relativized problems. Okay, so it will count the same kind of thing. It will count the input size, output size, but also count a third parameter, how many times you looked up the library or a dictionary. And so then the resources will be say that these are the requirements relative to this particular library or oracle that is given, kind of ready-made. And there is yet another parameters which is used quite a lot in algorithms, which are random numbers. They are not input or output, or they are not these oracles, but they are still some extra kind of resource. Very easy to say what a random number is, that every time you need a binary number, you toss a coin. No big description needed than that. But the question is, how do you define a mathematically explicit random number? And the answer is, well, you try very hard and you don't come up with any mathematically rigorous definition. In practice, it is fine. When you use it all the time, cricket match starts with a toss of a coin. And it's just an example that something which is the output, nobody could have predicted in advance. That is the important point. Nobody could have predicted in advance. there is no algorithm. And so this has a weird situation that mathematically you cannot guarantee them. What you can do is certification. These two words are used in the mathematical logic. What does certification do is nobody can predict it. It's a practical scenario, and as long as nobody can predict it, it is fine to use it. That is a certification. But it doesn't tell you that in principle there is no way to figure out what is going on. Maybe there is. It's just nobody is smart enough or clever enough to construct such an algorithm. And so yes, these are yet another kind of arguments which are well used in the algorithms. And when you use it in computer programs, most of them are constructed by some implicit algorithms by doing some arithmetic inside addition, multiplication, shift of the variables, all those kind of things. They are random, they look random to you because you don't know how they are produced. Yeah. Yeah. That's exactly the point. You don't know what is the dynamics of measurement. Suppose somebody figured out what is happening in the measurement, then all the mystery will be disappeared. It will be gone. So yes, if you put an axiom that fine, something is random, you have to be very careful about what is the meaning of random. It's not that easy to define. You can define probabilistic statements, but that's it. It doesn't say that somebody smart enough in the future with all kind of new techniques cannot figure it out. And like tossing a coin. Suppose you are given the initial state and all the collisions which are going to take place with various molecules in the air before that thing comes down and how it falls on the ground, etc. All the data is known. Maybe you can predict how it is going to show up on one side or the other. But you don't know all the details. And that is why, for practical purposes, it is something which can be certified. So yes, this is another feature, and today's time is kind of over. So in this particular context, in the next class, I will now define explicitly various labels which are used in the so-called classification of problems according to computer science. What is polynomials, what is super polynomial, what are in between, any new things which appear in terms of oracles, in terms of random numbers, all those kind of things.